Okay, let's start with this topic. This is very important topic so that we can design properly our structures against earthquake or seismic forces. So this is just basic, and we can learn later na based on an NSCP, there are seismic force resisting systems that are permitted and not permitted depending on what zone are you. So mostly we are in zone 4, so there is much there is some not permitted resisting system. But first, let's understand what is this seismic force resisting system. So as you can see, based on this based on the title, it is systems that resist earthquake or seismic forces. So it's important that in designing structures, it is not only designed to resist gravity loads such as dead loads, live loads, etc. But we should design our buildings or structures that need to resist the earthquake and seismic force. So now let's continue. What are these systems? First, let us define what is a seismic force resisting system. So as you can see here, these are structural systems or just part of the structure that specifically is designed and detailed to resist the earthquake-induced forces, example, lateral forces, story drips, or overturning moments in a building or other structure. So the goal here is we need to design safely this structural system so that our building or structure will be safe and according to code, or especially in NSCP 2015. So let's go. So first, let's define the basic system. So we have 5 basic systems of seismic force resisting systems. First, the bearing wall systems. Next is the building frame systems. Next is the moment resisting frame systems. And next is the dual systems. And finally, the cantilevered column building systems. So we will discuss this, and at the end, I will show you some building systems that is defined in NSCP, particularly in table 208-11. Okay, so let's start. No, so what is a bearing wall systems? So bearing wall systems, from the word bearing wall, is that the system only consists of walls that is located along exterior walls, and these walls carry the vertical load, and also these walls is the only seismic resisting elements in the system. In short, bearing wall systems has no frames. So mostly frames are also used to carry vertical loads, but bearing wall systems has no frames. It only carries it only consists of bearing walls or shear walls, and these shear walls and bearing walls are both resisting the vertical loads, and they are also the seismic resisting elements. So they both resist earthquake and gravity and live loads. So as you can see here, gravity load, lateral load, no, it's just an example. So this lateral load is based on soil. Sorry, I just get it from from the internet. So by the way, don't bother this one. So this is an example of lateral load of soil or water, no. But anyway, so as you can see here, this is an example, no. This is an example of bearing wall system. As you can see, we cannot find any frames here. So the one that resists, so the only element that resists both the vertical load, no, both the vertical load and the seismic loads, is only the shear walls or the bearing walls. Okay. So as you can see, the problem with bearing wall system is that there is no redundancy, meaning there is no redundancy that if the system fails, then it will be unstable. So it's much better to design structures with redundancy. So what are the redundancy? We can say that these bearing wall systems, if we add frames, the frames, although they will not resist the earthquake forces, they can still resist it after the bearing wall system collapse due to earthquake. No. So anyway, the redundant there is the frame. So next, that's what we are doing here now. The next building frame system is This is the one with the redundant frame system. So this is much better than building frame systems are much better than the bearing system, the bearing wall system. So this system uses a complete three-dimensional space frames to support vertical loads. So the space frame are there to support the vertical loads, but the main resisting elements to resist the seismic forces are the shear walls or brace frame. So let's see some some pictures. So as you can see here, uh, so as you can see, the space frame resists, or the frame resists the vertical loads, but the shear wall here resists the lateral load. So take note of the take note of who of what element resists the lateral load, and what element, or the earthquake resists the earthquake load, and what element resists the vertical load. So the element that resists the vertical loads are the frames, and the one that resists the earthquake or seismic loads or forces are the shear walls or brace frame. So as you can see here, there are bracing, and these are the examples of bracing. So brace frames, and this is the example of shear walls. Okay, this is much better than the what we call that bearing wall system, because in bearing wall systems there is no redundant. So here, the redundant here is the frames. So they call it redundant because the frames are not usually used for seismic forces. That's why they are said to be redundant. But that's good, because when the shear wall or the brace frame fails or collapses, uh, the space frame may, or it can help with resisting the seismic forces. So building frame systems are much better than the bearing wall systems. So moment resisting frame systems, no. Additionally, bearing wall systems has low R, or what we call the overstrength factor, compared to the building frame systems, no. So take note of that, no. So that we can see later in the NSCP that building frame system has higher uh, overstrength factor than the bearing wall system. Also, uh, the bearing wall system has higher amplification factor. I think they are almost equal with the building frame system, but the building frame system has higher overstrength factor, I mean. Okay, let's go to another moment resisting frame systems. So moment resisting frame systems has no shear walls or brace frames that resist seismic loads. Therefore, the only thing that resists the earthquake load and the vertical load is the space frames. So as you can see, if we compare the moment resisting frame systems to the bearing wall systems, is such that the bearing wall systems has no frames, only walls, and moment resisting frames has no walls and brace frames. So take note of the difference between bearing wall system and moment resisting frame system. So building frame system, the building frame system, the previous is here is that the frames are just used for vertical loads, no. They are not hybrid. Later we can know the hybrid part, the dual systems, but let's see what's the difference between them. So moment resisting systems again. So moment resisting frames really rely on the rigidity of their joints, no. So it's very important that these joints are being designed well. So as you can remember, in our discussion about uh, plastic moments in steel, uh, there will be a formation of plastic hinges since it is moment resisting. As you can remember that if the structure is resisting moments or bending moments or flexures, there is a time that plastic hinges form. So we need to properly and carefully design our structure such that the formation of plastic hinges will not cause structural failure or structural capacity. So plastic hinges is really inevitable if the design or the demand or the earthquake load exceeds the strength, no. So that's plastic hinges are formed from by resisting moments or flexure. So this is why we call moment resisting frame. So let's see illustrations here. So as you can see here, moment resisting frame system rely on rigid connections. And as you can see, of all these joints or connections, there will formation of plastic hinge soon. So we need to design properly and carefully such that plastic hinge shall not form, because remember, moment resisting frame systems has no shear walls or brace frames to resist seismic loads. And as you can see, moment resisting frame systems has higher, no, has higher, what we call that, higher overstrength factor compared to the building frame system or bearing wall systems. So for me, moment resisting frame systems are good because they do not only have the they wala silang ano ba, wala silang shear walls or brace frame that can makagulo sa design ng architect, no, sa architecture. So it's just plain frames, but you need to design it, no. And later we can see what are the moment resisting frame systems that are permitted in our zone. So these are an example. So this is just pure three-dimensional space frames, no. Okay, so we need to rely on the rigidity of the beam to column joints. So the hero here is the joint. So remember, if you are designing structure without shear walls or brace frame, remember that moment resisting frame systems has what we call that beam to column connections, and we must design, carefully design and properly design where the formation of plastic hinges, no, where the plastic hinges should form. So let's go to the dual system. So what is the difference between the dual system and building frame systems? So in the dual systems, there is a shear wall or a brace frame and frame. So in the building frame system, there is also what we call that frame and also shear wall or brace frame. So what's the difference? So then the dual systems, as you can see here, we can only classify the structure as a dual system if the space frames carry or resist at least 25% of the total seismic load for the entire structure. So dual system uses two systems from the word dual. The primary system must be the shear walls or the brace frames. We cannot consider dual systems if the primary system is the moment resisting frames and the shear walls are the secondary system. So in the dual systems, the main or the primary system or elements that could resist the earthquake loads or the seismic demands is the shear walls or brace frame. So the frames or the moment resisting frames is just a secondary seismic resisting elements, the space frames. So that's it, no. So but before we can consider the structure as a dual system, the space frame of the moment frames must at least resist 25%. Okay. So sir, what if the moment frames resist 100%? So I think it's also a secondary one because our primary is shear walls, no. So but that design is, but if we design the moment frames to resist almost 100%, so both the shear walls or brace frame and the moment frames, one of them is very redundant. So we must design the moment frames to at least resist 25%, maybe 30% or 50%, but always remember that dual systems primarily uses shear walls or brace frame. So the moment frames is just a support to the as a resisting element to the earthquake or seismic load. So remember the difference between the building frame systems, the second one I introduced you here, is that building frame systems only has shear walls or brace frame to resist earthquake loads. In the building frame systems, the column is the frame only supports the vertical loads, the gravity or live loads, no, dead load, live load. So in dual systems, both both the shear walls or brace frames and the moment resisting frames resist the earthquake loads. But before we can consider it as something na dual systems, the moment frames must resist at least 25% according to section 208.4.6.4 of NSCP 2025. Okay, let's see some pictures here. So as you can see here, moment resisting frame, then brace frame, then moment resisting frame, then shear wall. And these are some examples, sorry, examples, no? So let's continue to the final seismic resisting system, that is the cantilevered column building system. So what is this cantilevered column building system? So as you can see here, the main resisting force is columns or large columns cantilevering, no, from its base. So this is very very weak system, no? So you can see the overstrength factor of cantilevered building systems. Later you can see that uh, it's the smallest of all overstrength factors. So don't use this as long as other systems are permitted, but uh, this system exists because of architectural and urban design requirements, no? So let's see some examples, because there really is an existing cantilevered column building system. So the columns cantilevering from its base. So we can see the basic we can see some examples that in Chicago there is a cantilevered column building system, and that is the Marina City Towers. And in Mexico, we have a Torre Cube. As you can see here, there is a large column or columns cantilevering from its base. Diba? And in Marina Towers, you can see some columns here supports the entire structure. And they are considered as cantilever built column buildings. And I found this picture in an internet. I think this is also existing. So you can see here we have a very large column cantilevering from its base, and I think this can be done, but always remember that cantilevered column building systems has very very low overstrength factor. So anyway, okay. So before we end this topic, we go to the NSCP 2015 and see the different basic see the different basic seismic force resisting systems. So okay. So this is to table 208-11. So for concrete. So remember for concrete, diba? Okay, for concrete. Let's see what are the resisting systems. So we have the bearing wall system. So we have two types of bearing wall systems. I don't know why is this they almost have the same special reinforced concrete. So I will not discuss here how we can design special, ordinary, intermediate, etc., because that's outside of this topic, no. There are design or detailing guides or standards on how we can design or how I can say that this is special, ordinary. So you can see here in bearing wall systems, we have this what we call R, that's overstrength factor, and this is the seismic amplification factor. So as you can see here, the bearing wall system has only 4.5 overstrength factor. Meaning ng overstrength factor is this is the factor that we use to lower the lateral force or the demand, no. So as you can see earlier, as you can see in the previous sections of this NSCP 208, section 208, let's see here. Okay, as you can see here in the design base here, we can see that we have an R. So this R is the overstrength factor. So instead that this V is fully 2.5 CA times I or CV I times W, we can see that this design base here is divided by a certain factor that is greater than 1. So therefore the design base here is what we call that is reduced because of this overstrength factor. The higher the overstrength factor is, the lower the design load, no. As long as we carefully design this system according to this NSCP standard. So We compare this one, no? Like I said earlier, the building frame system is much better than the bearing wall system because it has higher overstrength factor, and as you can see, has lower amplification factor. So amplification factor is used to amplify the load, no, in combination. So let's see which force resisting system has higher R. So we go to the moment resisting frame systems, and we can see that both 8.5 here and also 8.5 here are used for dual systems. So it's up to you. So I suggest you use special reinforced concrete and special concrete shear walls. So but first let's consider this NL, NL, NP. So what is this NL? So NL means no limits. That is NL. And NP is not permitted. Yan. NP means not permitted. So not permitted means you cannot build structure that is this type of seismic force resisting system. So in special reinforced concrete shear walls, we can do special concrete shear walls. So let's see, no, if we focus only in zone 4, because in zone 2 most are no limits. Only this shear wall frame interactive system blah 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 is not permitted in zone 2. So in zone 2 we can build any systems we want based with concrete as the material, no. So as you can see here, the special reinforced concrete shear walls is permitted up to 50 meters only. So there is a limit of up to 50 meters. So ordinary reinforced concrete shear walls is not permitted. So let's put X here so that we can see this is not permitted, this is not permitted. Then the special reinforced concrete shear walls or brace frame, so it needs to be special. So the limitation is only 75, and the ordinary is not permitted. So this is not permitted. You don't build a structure that is ordinary reinforced concrete shear walls or brace frames. So intermediate precast shear walls are permitted up to 10 meters only. So we can do that, no, for building frame systems. So in the moment resisting frame systems, this is very good, the special reinforced concrete moment frame system. And that's why I urge you, for structures you are designing that is less than 10 meters, 10 meters, sorry, 10 stories, I mean, we should design it using the special reinforced concrete because it has higher R and decent, no, mostly decent, no, decent amplification factor. So this is permitted, no. So not only permitted, but it has no limits. So we can build special reinforced concrete moment frames any height or any stories. So as you can see here, sorry. So so intermediate and ordinary reinforced concrete is not permitted. So this is beyond the discussion here. But always remember that there is a provision in NSCP that we need to design special reinforced concrete moment frames, and there is a guide here to design these special reinforced moment frames. So we go to the dual systems. So ordinary reinforced concrete shear walls is not permitted. So not permitted. But the special, same with this one, special. So dual systems, special reinforced concrete shear walls and moment resisting frames has the same R and omega. So they are almost the same. So you just choose. It's either special reinforced concrete shear walls or special reinforced concrete moment frames. So that's it, no? And always remember, the bearing wall system and building frame systems has limitations. So remember that. So dual systems with intermediate moment frame, so mostly not permitted. And for special reinforced concrete shear walls, if the system has intermediate moment frames, no. So this one, the dual system here, is special moment frames. So we can only use this if we have moment frames that is special reinforced. So the special here is the shear wall, but the moment frames, the secondary, remember, dual systems has a secondary, and the secondary one is the moment frames. it is permitted up to 50 meters only. So let's remember that. Then we have this cantilevered column building system. Okay, so cantilevered building column system is limited only to 10 meters now. So shear wall frame interaction system, I did not bother that to discuss because in steel there is no such thing there. So I just only discuss the most common or basic. So we have 5 A, B, C, D, and E. So okay. So D and E here is the same, almost the same. So F is the cantilevered column building system. So let's go to the steel. So this one is concrete. So in steel, you can see here that this is 2.8, sorry. This is 2.8, this is not 28. So 28 is so much. So for building frame system, we have also 8. Moment frame resistance 8. So no limit. So you can see here, we have some limits here. You can just check here. For steel, for masonry, okay, we have only 4 types: bearing wall, building frame, moment resisting frames, dual systems. So we have, I think, a masonry moment resisting wall frame. So uh, I really did not see any existing here, but this is good, no? This is also good because it has 6.5. No, so this is focuses on masonry in the hollow blocks, etc., bricks system. So we also have wood. So although we don't too much focus on wood here in the Philippines, but we have two systems, the bearing wall systems and the building frame systems. So they are permitted up to 20 meters in zone 4. So you can rely on these NSCP provisions, and please follow the limitations and permissions if we can really build these systems. So I hope that you can design your buildings according to the NSCP standard so that we can have a strong and resistant, earthquake resistant buildings. Thank you and God bless. Okay, let's go back here. Thank you and God bless. So building systems. So don't forget this building system.